Okay, let's get started here. So today we will continue with the graphics section, and we'll also review for test number 1. I do want to really briefly talk about project number 1, which we would talk about in more detail next week. This project is going to have you apply what you learned in this graphics section that we just started, and also the next set of notes on principal component analysis. Apply it to a data problem essentially of your own interests. So, obviously many of you are already engaged in research, so you may have a particular data set that you'd be interested to explore further in the context of our course. Given the size of our class isn't too large, I think it's at least manageable for me from a grading point of view, that I don't have to give you a particular data set and have everyone in the class use it. Rather, I can deal with a number of diverse sets of data. So, again, for these particular 2 sets of notes, you can use your own data to basically demonstrate to me that you understand the corresponding material. As you will see next week when I give you the project, you're going to see I have some guidelines about, okay, I want you to show me how you can do this, how you can show me how you can do this, how you can show me how you can do this, something else, with respect to your data. Now, also I understand that some of you maybe don't have some of your own data yet that you can use, or maybe you don't have easy access to data. You have no idea what to use. And so you're welcome to go to like a multivariate statistics textbook. Obviously gave you a few references on the syllabus, and use a data set from there. The key with any data set that you use is that I have to actually approve it beforehand. And so next week, actually on Tuesday, I'll give you some more guidelines about how I would actually approve it. Simply email it to me, give me some information about it. Now for these projects, I like you to work in groups of up to 3 people for it. So I think you can not only learn on your own, but you can learn a lot from your fellow classmates. So what I will have for our week number 5 quiz is basically a group member sign-up. So I guess Wednesday of next week, you'll simply take the weekly quiz that we've been normally taking, and you'll just indicate to me who your group members are. And if you do that, you get 5 points, just like with the other quizzes. Okay, so more on this next week, but I wanted you to start thinking about potential data, potential group members. If you don't necessarily know who you would like to work with in a group, it's okay, because I understand not everyone knows everyone in the course. I have a mechanism that I will use to help put you in a group if needed. Okay? Are there any questions about that? Okay. Any questions in general before we get going here? So, at most, I like to spend about 30 minutes going through the graphics section, and then we'll talk about the test some more. So the first thing that we're going to talk about with respect to the graphics section here is how you can get basically 3 variables on a plot. And so let's begin with, of course, 2 variables. Well, we can do a simple scatter plot. So if we go back to our serial data with the serving size adjusted variables, sugar, fat, and sodium, what we can do is a scatter plot of, let's say, sugar and fat. We've done these kinds of plots before. So the main thing is you have an X argument where you pull sugar out of cereal. You have a Y argument where you pull fat out of cereal. And this is the plot that we get. So, the purpose of this graphics section is so that we can, let's say, detect trends in the data. Detect potential, maybe unusual observations with the data. So with respect to this plot here, do you see any trends? Do you see any unusual observations? terms of trends, remember that there was a Pearson correlation of about 0.25 here. So it would be probably difficult to see much of any kind of trend. Maybe we have some unusual things going on up here, because they're kind of separated from the rest of the points. So how about we add another variable to the plot? That might help us see some trends, so that now we have 3 variables in our plot. And so what I'm going to do is have the shelf of the serial correspond to the plotting point in some way. There are a number of different ways to do that. You could change the color of the plotting point corresponding to the shelf, the size of the plotting point, the actual symbol that's being plotted as well. These aren't necessarily surprising. I'm going to do all 3 of them here just to demonstrate how you could do that. So imagine, I could just do color here to get a 3rd variable in the plot. For a 4th variable, I could do the size. For a 5th variable, I could do the symbol if I really wanted to. Again, this is a multivariate class. We want to see how we can examine trends amongst multiple variables at the same time, and this is how you can do it. Now, when I was going through my notes yesterday, I was thinking, I could have done this plot slightly differently, and so that's what I'm going to do here. And then I'll come back to the way that I did in the notes just to show you how it's not that much different. Right before class, I uploaded a new version of this corresponding program that does have this different way of doing the plot. Okay, so first of all, if you remember with the shelf, let's see here. We have 4 shelves, and part of my, research hypothesis was that, grocery stores are putting different kinds of cereals on the different shelves on purpose, and we saw an example with my son Callum demonstrating that indeed maybe that occurs. And so I have this variable called shelf in my data set. Actually, let me look at the whole data set here. So shelf is 1, 2, 3, or 4. And notice how everything's ordered. I'm going to take advantage of the fact that it's ordered. And so what I'm going to do is create a vector in R's terminology where the first 10 items in it have a certain color to it. The next 10 items have a certain color corresponding to it, and so on. So I create this object called shelf.color. I use a function called REP. REP stands for repeat. So I'm going to repeat the colors black, red, dark green, blue, each 10 times consecutively. So if I do that, and just look at that, oops, there you can see that. Now just a little bit of a side note, because this does come up sometimes when one uses R. If I were to replace each with times, notice the difference, where it repeats all 4 colors, and then it repeats all 4 colors, and so on. Just a little bit of a helpful thing to know. Now, in terms of the symbols, I want to change the symbol based upon the shelf. Now, if you remember from the introduction to R notes, specifically when I was doing the regression example, R has already built in 25 different kinds of symbols, and the way that you refer to them is simply by number. So I'm going to make it easy and just refer to the first 4 symbol numbers. So I have an argument or object called shelf.symbol, repeat 1, TO, 2, 4, each 10 times. And we're going to get what we expect. Okay. Now, going to my plot function. Once again, X argument sugar, Y argument fat. Now, where I take into account the color and the plotting symbol is through the COL for color. So I put shelf.color there. Now again, remember there are 40 different experimental units, 40 different observations in the data set, and so R is going to match up based upon the ordering of the values in the data set, with going to match everything up with the correct color. So that's one way that you can get the colors to change. PCH stands for plotting character. Same thing's going to happen there. Now to change the size of the plotting character, this is not necessarily something that's intuitive. I can use an argument called CEX. And so what I'm going to do simply is that if I just use 1 there, that means it's the default size of the characters. You can see what it is if you just run it with 1 there. But what I'm going to do is take 0.3 times the shelf symbol. Remember, those are numbers. And so this will allow me now to have different sizes of plotting points relative to the default. So 2.2 times the default allow me to have different size of plotting points. Okay, so if I do that, there's my plot. And I should have a legend associated with it so I can understand what the plotting symbols correspond to. There's an R function called legend that allows you to do this. The X argument says where on the X-axis do you want to put it? Say at 0.5. Y-axis at 0.08. I can put a title with the legend. The legend values, well, I'm going to have shelf 1, 2, 3, 4, so I can just put 1, 2, 4. If I wanted to, instead I could have done this. This is helpful to know. If, let's say, you had actual names for the different levels that you're plotting. BTY stands for box type, equal N there means I don't need a box around my legend. Notice how I put the 4 different colors in there. I put the 4 different plotting characters and the 4 different point sizes for our points. So if I do that, here's my plot. So there you can see where the legend is. Now let me pop on over here back to Word. Okay. Now, so again, the purpose of doing this plot so that we can see trends, so that we can see unusual observations. Do you see any trends here? There's one that I can see now that I wasn't able to see before with the previous plot. And don't think of necessarily as a linear trend as the only kind of trend that you could have. I'm going to draw a line right down here in the middle. Maybe that might help you see it. Excuse me?
The triangles are on the right side.
Exactly. Shelf 2. Look where shelf 2, relative to sugar, where those observations are falling. And remember how what we said with, I guess, my original research hypothesis is that these grocery stores are putting maybe these higher sugar content cereals, which typically correspond to kid cereals, on the lower shelves. Shelf 2 was one that was easy that my son could actually reach from. Well, now you might be wondering, well, what about shelf 1 then? Because he could reach from there too. Well, unfortunately, it doesn't quite follow the same. Although we do have, I guess, 7 of the 10, I believe that, yeah, that should be 7 of the 10 observations that are to the right of that red line there. So it's kind of interesting to see that. Again, we see these particular observations up here. That's maybe kind of stand out from the rest. As we go along here, we would definitely want to look at, what those corresponding cereals are. And maybe we can figure out, oh, okay, that makes sense why they have much, well, I wouldn't say much, but they do have somewhat higher fat content than those other cereals. If we, essentially it's about 25% more fat content. Okay, so let's move on. So the previous code took advantage of the data being sorted by shelf number. Now, if it wasn't sorted by shelf number, we might want to actually sort it that way so we can take advantage of this. Even if you, well, I won't go there, but let's talk about how we could, let's say, unsort the data and then sort it again. Now, one reason why I want to go over this is that very often in any kind of setting, you often want to sort your data a certain way so that maybe it helpful for plots, or maybe it's helpful for other circumstances. And it's not intuitive for how to sort in R. Right? There is a sort function, but it's not useful with respect to a full data set. Okay, so how can we unsort the data? Well, what I could do, since I have 40 different observations, how about if I take a sample from 1 to 40, a random sample, without replacement, and I do this simply with the sample function. Notice for the x argument, I have 1 to 40 there. Size meaning, well, how many observations you want to, or how many samples do you want to, or what's the sample size for this 1 to 40? Well, I just put essentially 40 there. That's the number of rows for serial. And so now what we see here is you could say maybe a potential different ordering of my data, where the 4th observation comes first, the 39th observation comes second, the 1st observation comes third, and so on. But I want to be able to always replicate this, at least in a classroom setting. So suppose I set a seed so that when I do this, I always get the same result. And this is what I have then in my actual notes. And so now, if I take this new dot order and put that as the row number designation for serial, well, look what's going to happen here. Is now the 14th observation shown first, the 36th is shown second, and the 1st is shown third. So it just reordered everything, jumbled stuff up. Now, if I wanted to put everything back in the same order, original order, the first thing that you can do is use the order function. Let me just, unfortunately, I skipped this. Serial 2 now is my new ordering of the data. And so if I say serial $2 $shelf, what I have here is the corresponding new ordering of the data in terms of by shelf. If I want to order it correctly by numerical order, I can use the order function. Or I'm sorry, this doesn't give me that exactly. Just a second here. Okay. So, and I sometimes have to think twice about this. And in fact, this was just one of these occasions. And even when I was going over this in my notes today, I was like, okay, I had to remember exactly or yesterday, when I was going over the notes, I had to remember this. Okay, so what this order does here, this 3 represents that the 3rd observation, if I were to sort everything, should come first. This 4 says the 4th observation should come second. Notice how it's shelf 1, shelf 1. Okay, so that's how that works. So if I take this new ordering as the row numbers of serial 2, I can form a new data frame called serial 3 that does have the correct ordering. And now I could go ahead and use my functions that I was using before to do the plot. Okay, any questions about that? Now, this is not in the notes, but I think this is helpful to understand. Let's say if I didn't want to go through the process of sorting, and I wanted to simply assign the colors by the shelf number. Okay? There's a few different ways to do it. I'm going to just show you one. This is useful to know. I can use an if-else function. All of you have had some kind of programming experience before. There's often an if-then control statement in any language. And in R, there's two versions of it. One's called if-else. So if I say if-else test equal, I'll just go with my original data. Test serial $shelf equal 1, comma. If that's true, then I'm going to assign it something with, what's the first color? Black. So the yes means, okay, if it's true, make it a black. Now this isn't the most efficient way to do this, but what I could do as well, notice if I'm just going down to the next line, it's not changing anything. And I'm just doing this so that you can see this better. Now for no, how about I do another if-else function. I do almost exactly the same here. And suppose I make that red. I do it again. Oops. Let's see. Dark green. Oops, actually I don't need to do that last one. So basically I have what are called nested if-else functions here. So if the shelf is equal to 1, if that's true, then black. Otherwise, go to the next if-else. If it's shelf 2, make it red. If no, then if it's shelf 3, it's dark green, and there can be no other shelf numbers. I have checked this in the data set, so everything else is going to be blue. And so if I run that, that's another way you could get all the colors as well. So that is a helpful thing to know. As a way to do this. Okay. So let's look at another way that we can get a third variable on a plot. We can do what's called a bubble plot. And basically this is just simply a scatter plot where the size of the plotting point grows as, or the size of the plotting point is proportional to the size of the third variable. We kind of just saw that with the serial data set, but this is a more general way, with the last set of plots, but this is a more general way to do this. Okay, to do bubble plots, I can use the symbols function for that, where again for my x-axis sugar, y-axis fat, and then for my third variable, I can say circles. I'm going to actually plot circles as my plotting point, and the size is going to be proportional to the size of sodium. So all the other arguments remain the same as what we've seen before, and this is what I get. And so we can see that we have a variety of different sizes of plotting points. In fact, some of these plotting points are really too large. They're really, really overlapping. It's hard to make sense of this. So there's an argument that you can add called inches. And this controls the size of the largest circle that is there. And so if I say inches equal 0.5, now we get something that's a little bit more readable. So let me come back over here to my notes. Just see. So there we go. So again, sodium is that third, or is the size of the plotting point. Where is the smallest sodium values? Just give me a, like, is it lower, is it upper left, is it lower right? No, lower right. It's not lower right. Right there. I know they're hard to see. These are actually sodiums that have a value of 0. So this is important to understand because different software packages do these kinds of plots differently. In R, you will still have a small little point if you have a value of 0. For those of you who maybe have experience with SAS, SAS won't even draw it. So we can also see where the largest sodiums are as well. So that's kind of interesting that some of the largest and some of the smallest have low sugar and low fat content. Let's see here. Now, you might be wondering, okay, well, which of these, what are these actual, let's see what I do first. What are these actual cereals that we're talking about here? And so what we can do with R is use a function called identify, where my x argument is sugar, x and the y argument is fat. And what R will do by default with identify is allow you to click, left click, on particular observations in the plot, or plotting points in the plot, and identify what their corresponding observation number is. You can actually use identify to have something else pop up when you left click. You can take a look at the help if you're interested. But you can see how that can be helpful, especially let's say if you're identifying, you want to see, okay, what are these points out here that maybe are a little bit different from the rest? Now notice when I ran that identify function, my mouse, notice now I'm in the console window. Now when I come over to the plot, it becomes a plus. Why? Because it wants you to add information to the plot by clicking on the corresponding point. Now to get out of this so that you are no longer adding points, I can left click, stop, or you can hit escape on your keyboard. And so what we can do now is come back to my serial data set. And if I want to take a look at, let's say, 8, 20, and 25, we now have a quick way to know more information about, well, what are these cereals that tend to have this high fat content? Okay. Now, 2 of those cereals there have something in common. Can you tell but from the names? No, we're running out of time, so I'm just going to go through this more quickly. They're nut-based. Of course, nuts have healthy kind of fat. They do have a lot of fat in them. Okay? And so that's why we're seeing that. And then we have these Oreos. That's a really probably unhealthy cereal there. That just happens to have a lot of fat in there as well. Notice also it seems to have a considerable amount of sugar too, which you expect from that kind of thing. Let's take a look at the cereals that have no sodium. These are the shredded wheats. So if you've ever had this kind of cereal, basically it's a very blah tasting kind of cereal that's just based upon, it's the only ingredient essentially is wheat. That's it. I should identify what these ones were in the bottom left-hand corner here. Maybe you can do that on your own. These large sodium content cereals to see what they are. We're running out of time, so please go do that on your own. Check to see what they are. Okay. Now, for those of you who are using RStudio, though, note that there is a flaw with RStudio when using the identify function. It won't actually allow you to, let's say, click on a plot to do that. So to get around that problem, what you can do is use dev.new. I might put that in, I think I did put that into the introduction to R notes. Dev.new stands for device new. And what that's going to do, if you run that, it's simply going to open up a new graphics window. And we'll open it up, if you run it in RStudio, we'll open it up outside of RStudio, and that's where your plots will be directed, and you will be able to click on them. So here's a question. What would happen if there were both positive and negative values for the circles argument in terms of what variable you put there? Again, the plotting point is proportional to the size of the whatever variable you're putting there for circles. And so it's easy to think about it in the context of when you have positive values. But what if you have negative values? It's actually going to produce an error. So think of this, let's say if you had standardized data, you will have negative values. Then you're going to need to adjust that data so that everything's positive. So you could add like a small little constant to it. Now there's alternative ways that you could identify points too. So for example, if I use the text function, where my x argument's sugar, y argument's fat, then I can actually plot particular labels automatically for all the points on my plot. So for example, maybe I want to plot my sodium values rounded to 2 decimal places, and this is what I would get. And so now this helps you see what those sodium values are in the context of what those bubbles are saying. Some of this is minor, so I think it's okay that I go through it more quickly. There are times where where you might have a lot of, let's say you have a lot of observations, and you only have a few that have very large values in comparison to the rest. What's going to happen then on your plot is something like this. So maybe these are the large ones. And then since there's such a small difference, or such a large difference overall between these points, all the other observations are represented very small. And so it's in this kind of a case, the plot may not be very meaningful. I mean, imagine if you had a very large observation like that. Okay, so what you can do, a simple fix to that is just simply rescale whatever you're putting in for the circles argument. So what I've found in the past that often works is to use simply a square root. And so what that's going to do is move things closer together than what they would have been before. So imagine, let's say if you had, let's say, values in your data set of, let's say, 9, 25, 100. Now if you take the square root, now you have 3, you have 5, and now you have 10. And so these are tricks that are very helpful when doing these kinds of plots.
Can you use log?
Excuse me?
Can you use log?
You could use log too, but then you're going to have to worry about if you have negative values. And so then you might have to do another kind of add a constant. And lastly, well, let me see here. Yeah, I'm going to just stop. If we have time at the very end, I'll come back to this. Okay. Okay, let's talk about the test. Okay. I briefly talked about the test already before, so a little bit of this will be reviewed. So the material for the test is up to the data distributions and correlation notes. So the stuff like we're doing today is not going to be on the test. It's closed book, closed note, closed video. So you cannot use books, you cannot use notes, you cannot use our corresponding videos for our classes. Of course, you cannot talk to your classmates. You cannot communicate with anyone outside the classroom while you're taking the test. Now, what you can use is my R programs, because I don't want you to have to memorize R code. But you should be familiar with what the proper R code is if I say, go do a scatter plot. Okay, well, it's a plot function. Okay, if you need help with some of the various arguments with the plot function, well, you think, okay, I remember us doing a plot in the GPA dataset program. So I can go there, I can copy and paste that code into my new program that I'm writing, let's say, for the test, and make some corresponding changes to it if needed. Also remember what I told you about last time is that on the graded web page of my course website, there's a formulas and functions PDF. You can use that as a quick reference as needed during the tests so that you're not always flipping through your notes. I mean, I understand, I'm sorry. Excuse me, you're not flipping through your notes. Excuse me. I don't want you to have to memorize formulas. I don't want you to have to memorize functions. Now, through the semester, though, of course, you're going to be using some of this stuff, so some of this stuff will be familiar to you, but you shouldn't have to memorize it. Also, you're welcome to use the R help that is with R itself. Don't Google, how can I do a scatter plot when you're taking the test? That would be something that you can't do. But you can use the built-in R help itself. Any questions? Is it clear about what you can and cannot do on the test? So the test is being taken in this classroom. You'll use the computers here. I strongly recommend that before you leave here today, just make sure you can log on to these computers. I mean, it's just your normal UNL AD account login and password. Make sure you're familiar with the fact that RStudio is on these computers, where you can find it. It's just a normal Windows-based computer. It can take a little bit of time to log onto these computers sometimes, so I strongly recommend that you log on to the computers before we start the test so that you're ready to go. Now, at times, computers can have problems. So, I recommend, most of you probably have one, bring a laptop with you, just in case something goes wrong with the computer here or computers in general. Have a laptop with you. If we find that you cannot use the computer that's in front of you, I'll let you use your laptop. You just don't access your notes. You'll just have to be on your honor. You may need to install packages during the tests. Remember, unfortunately, RGL does not work on these computers. That's disappointing. Given that I didn't discover this until last week, I decided it wasn't worthwhile to contact ITS to see if we could have these computers fixed. So you don't need to use RGL for the tests. There may be, let's say, stuff that I create with RGL on the test, and you'll need to interpret it in some way. So the test will be available on the graded web page of my course website. So when the test begins, I'll say, okay, you can go ahead and go download it, start the test. That's the way we'll do it. It will be simply in a Word file. And we will start at 8 a.m. Put all your answers in this Word file. Something we mentioned at the very end of the last class is that you can use text-based expressions for symbols as needed. So, for example, if you need to use, if you want to do mu hat for some reason, it's okay if you just put M-U-H-A-T. I encourage you to use the equation editor, but I understand that students are at a variety of different abilities or experience with using the equation editor in Word. In fact, I don't like the equation editor that's built in Word. That's why I use something else called MathType, and I use as an add-on to Word. So you don't need to use the proper symbols. But if you were to, let's say, only put mu there when it was meant to be mu hat, I would take off points. So you do need to include that extra part there, because there is a difference between mu and mu hat. Email the test to me by 9:45 a.m. So I'll have my email up, and I'll be monitoring it, obviously. And once I receive your test, I will say, okay, or I will email you back, say, I got it. Then you can leave the room. But don't leave the room until you verify with me that I've gotten the test. And what I have found in this kind of a setting, usually we usually have a larger class or larger number of students. Usually the best way is simply for me to reply to you rather than say, hey, I got your test. I got your test, So Do note that if you email it to me via Gmail, I have found that there's often like a 10-minute delay for some reason. Well, I have a Gmail account, I don't usually use it. Perhaps there's a setting in Gmail that has an automatic delay of sending. And so I've had students say, I sent you it like 5 minutes ago. You mean you haven't received it yet? I said, no, I haven't. And especially when we're at 9:45 a.m. At the end of the test, and I still haven't received your test, even though you've sent it, that is a problem. So I recommend don't using Gmail to send me the tests. Now, sometimes a problem for students is speed in terms of getting the tests done. You know, you need to be proficient in the ability to do, something like the R stuff. You can't take 20 minutes to figure out how to do a scatter plot. You should have had some experience already doing scatter plots, for example. And so, that should take 1 or 2 minutes at most. But if it's taking you 20 minutes, if you're, let's say, searching through my programs trying to figure out how to do some of this stuff, that tells me you haven't studied enough. So, make sure you think about, having the ability to do some of this stuff with some speed with it. Okay, any questions regarding the basic setup for this test? Okay, let's talk about the structure. As I mentioned last time, you need to show your work. Numerical answers without any additional information will not receive full credit. So whenever you use R, I want to see your R code with the corresponding output. I need to see that. And this is all for your benefit. Because if you were to do something wrong and get a wrong numerical answer, I can go back to look at your R code and output, or if you gave me some other information about how you were trying to do the problem, I can look at that as well. And maybe I find, oh, you just made a very simple error. So I'm going to give you almost complete credit for the problem. And so that's why it's to your benefit to make sure you show your work in some way through its R code and output or through other mechanisms, depending upon the kind of problem. So I have a simple example here. Suppose I ask you to calculate an estimated covariance matrix. And if you just gave me the covariance matrix alone, you would not get full credit. I want you to show me the use of cov, maybe some information before that as well that was needed. Show me the corresponding output within the corresponding covariance matrix. Excuse me. Sorry. So there are two different kinds of problems that you will find in my tests. If you take a test from me before, these are the same types. There's a type of problem that will have multiple parts that's usually concerning a particular data set. Sometimes it's not, depending upon the material that we cover. But let's say, you'll see an example shortly, but let's say I give you a data set, I have you do some, have you do one calculation for it. Then I have you do another calculation for it. Then I have you maybe interpret something corresponding to those calculations. So that would be one kind of problem. Now the very last problem on my test is a little bit of a different format. It will have multiple parts, and they're each short answer questions. Maybe it might have a calculation, maybe it will not. And these parts are not interconnected in any way. So to do part B has no relation to part A, where the previous type of problem, part B might rely on something in part A. Okay? So those are the types of problems, and I'll have examples of those shortly. let's do a little bit of a review for the test to make sure you understand what I think is important. We began with an introduction to R. The basics. What is an R function? How can you find information in the help? What's an argument? It's important to use the proper terminology with R. An argument, a data frame, a function, a vector. You need to know the proper terminology. Knowing that proper terminology will greatly help you elsewhere, rather than. Excuse me?
But you wouldn't ask us to define that function or something.
I could simply say, tell me what an argument is in R's terminology. Now, hopefully that won't be too difficult. What is a package? How do you install it? Then we also did a regression example. So on this test, I could ask you questions about regression. We've seen it in two different places, the introduction to R, and also with the matrix algebra part. So I could give you a data set, ask you to state an estimated regression model based upon this data set. Maybe ask you, could you put together like the X matrix for that data set, and maybe do some other corresponding calculations with it. That would be a potential question. Could you do a scatter plot? Then in terms of matrix algebra itself, the basic structure of a matrix, transpose of a matrix, doing addition, subtraction, multiplication. What is a diagonal matrix? What is an identity matrix? How do you find an inverse? There was a lot of things here. Trace, determinant, eigenvalues. Can you plot then the corresponding eigenvectors? And then lastly, in this data distributions correlation section, what is multivariate data? What's the corresponding notation that we use? What is our X matrix in terms of what we do in multivariate? We spent a lot of time on the multivariate normal distribution. There's a lot of characteristics about it. How is this an extension of what we could say is the univariate normal distribution that you've learned about before? What is the mean vector, the covariance matrix, the correlation matrix? What is the relationship? What is f of x in this context? If I gave you, let's say, a multivariate normal distribution, could you tell me what f of x is? Actually do the evaluation. Could you actually maybe write out the actual expression for f of x?
You mean the formula for that?
Yeah. Now, I'm giving you the formula. Remember? That's in the PDF for that formula as a function sheet. But could you actually write out, in terms of the matrices and the vectors, if I say, here's a covariance matrix, evaluated at this particular x value, could you actually write it out? And that I have given that kind of a question in the past, just to verify that you can do more than, let's say, plug it into the corresponding function in R. We spent some time talking about data simulation. A question that I asked you was, why is data simulation important? What would we expect to happen if I simulate data from a bivariate normal distribution? What should the values end up being? Let's say the summary statistics, like the estimated mean vector, the estimated covariance matrix. How could you check for multivariate normality? Why is there not a good way to do this? How to standardize data, and then let's connect all the eigenvalues and eigenvectors to the covariance matrix for multivariate normal. Okay, so that's a brief review of what I saw as the important topics. Let's talk about two actual questions from a past test that I've given in this class. Now, the one difference from where I picked this test from, the one difference in terms of the format was that students had a paper copy of the test and they actually wrote their answers on it. They still were using computers in this classroom to take the test. So there was a small difference, but not too much. So suppose that we have this multivariate normal distribution here. Okay? And in part A, for this particular semester, I actually gave 4 different plots. It was actually a multiple choice problem to some respect. Tell me which of these plots does this multivariate normal distribution correspond to? Okay? Now, the key was this. Explain your choice by specifying particular characteristics of the plot that correspond to the distribution. So this goes beyond, let's say, you actually doing the plotting yourself in R. You know, we have like maybe about 6 lines of code that one could do to do this plot. And that could be helpful for students to answer this problem, but it's actually not necessary. So, and unfortunately I can't get this all on. Let me see if I can move this up. There we go. Is this big enough that you can still see it? Yes or no? Yes. Okay, so I'm getting some yeses, so I assume it's yes. Okay. So we have 4 plots here, all on the exact same x and y axes. So, how could I figure out, without even doing the plot in R myself, which plot is the correct plot? Well, the first thing I would look at is that mean vector. Okay? And so if you do that, you will notice that this is the only one that's not centered at, let's say, the x-axis of 5 and y-axis of 10. Okay? So now I can use the covariance matrix to help me figure it out. So one of the things that I would look at is, well, do I have positive or a negative relationship? So based upon that covariance matrix, which one? Positive or negative? Positive, okay? Which of the plots show a negative relationship? Yeah.
Right.
That one, okay? Oops. Okay, so now I narrowed it down to 2. Now next. Excuse me. Okay. Notice that I have obviously a relationship that's above 0. And so for this one, let's take a look at this plot here. This would correspond to a contour plot that would have 0 as its dependence. Because there's no, let's say, slant to that ellipse. So then, this is the right answer right there. And so what I would look for then in your answer is kind of what I just discussed here. What characteristics I'm going for, or what characteristics correspond to this. So then part B says, roughly indicate on your chosen plot from A where you would expect most of the x1 and x2 data values to be for a random sample. In your answer, indicate where the concentration of x1 and x2 values would be the largest. Note that you should be able to answer the entire problem without actually simulating the data. So this is the actual code that's simulated. I just included that in the answer key when I gave this for the students. But what I'm looking for here is, students would just come up here, and do something like that. And here's an actual sample size of 100. Let me bring this down. There you go. Now, at first when I was preparing for this class yesterday, I was like, well, let me say it another way. Now, a different way I could have asked these problems would have been actually do the contour plot yourself. or actually simulate the data yourself. Okay. Just in this particular case, for this particular semester, because of other stuff that I had on the tests that I knew could take some time, I decided to do some of the work, essentially, do some of the code for you, for the student, and give the plots themselves. Now, then, on the plot chosen for part A, plot the vectors for the covariance matrix. Scale the eigenvectors so that they have a length of 5. So, how would I do this? Well, I would create an object in R that contains my covariance matrix, call it sigma. I would use the eigen function, get the eigenvectors out. To have them a length of 5, well, I just multiply them by 5. Now, if you wanted to, you could actually use the arrows function and do the plot yourself. But in actuality, you could just simply plot it you could plot it without actually doing it. So this problem is a little bit, how should I say? Well, I guess the key is to demonstrate that at times I could ask you to do everything completely by R. Other times, you could do R, but it might be faster not to use R. And this is one of those times. And then corresponding to a question that we had earlier, find f of x at this particular value of x1 and x2. Actually find it. Actually set up the expression for f of x. And so what I did, or what you could do is, go to the actual formula sheet and set up the equation. Do that. Go to dmv norm, that function, and get the corresponding f of x. That would be the quickest way to do it. Okay, so that's one of the first type of questions. This one doesn't actually have a data set necessarily involved with it, but you can see how all the problems are interconnected in some way. Now, another kind of problem would be then where, let's say if I have maybe 4 or 5 short answer questions that are not interconnected at all. Here's an example of one potential short answer question. What is the difference between using the asterisk and the percent asterisk percent with matrices in R? Can someone tell me what the difference is? One does matrix multiplication, in particular this one, and the other one does element-wise multiplication. For those who are fairly new to R or have never done anything with matrices before in R, this is an easy way to get tripped up when you use the asterisk, because you would think, okay, that's the way I'm going to multiply matrices. In fact, in some programming languages, that is the way that you do matrix multiplication, but not in R. Okay, so we have 15 minutes left. Do you have questions? Yes?
For example, for this type of questions, we don't know how to explain it. We have a lack of English, words. So can we explain it with example?
You need to be able to explain it in English. Sorry. So this is from the actual answer key. I mean that's one sentence.
Yeah, okay.
But you do need to be able to explain stuff in English, because think about obviously depending upon what you or others want to do after you graduate, you might be in an English working environment. Okay. Was there a question over here? Okay. Are there other questions? Now, my hope with this test is that it won't be difficult. Well, I hope that with any test. But at least the way that I set up this particular class this semester, and I've used this format of having this early test now. This is the 4th time I've done this. It seems to be helpful to students to do this because, generally speaking, most students will do very well. It gets them off to a good start. And for those few students who don't do well, this says, okay, this is a warning. Unfortunately, it's not going to hurt my grade too much because it's only 5% of my overall grade. This is a warning that I need to do some changes. And so you can figure out what those changes are that you need to make on your own. Maybe some of them will be obvious, but you're also welcome to talk to me if you find yourself in that position. Of course, I want everyone to do very, very well here. Before our test on Thursday, you're welcome to talk to me about any of this material. Take advantage of the discussion board that I have set up on Canvas as well. Any other questions? Okay, let's see if we can at least get through this bubble plot set of notes, and then we'll call it a day. Okay, this is something I wish I would have put in the actual code and plot. I wish I would have put in the notes. Is how can you add shelf type to this plot? What would be one thing that you could do?
Color.
Yeah, color. So let's go ahead and do that. And I did not. It's in my program, but I did not unfortunately include it in the notes. And so a very simple way to do this, and it's not necessarily intuitive, is you have the FG argument in the symbols function. FG allows you to add color to it. I don't know, maybe it comes from the word foreground, but I don't know. I don't think that's a perfect explanation. And so here we go. There's the plot with the corresponding text as well. And so now, again, and unfortunately I didn't have a legend on there. I should have, excuse me. But, we can see again how those high sugar content cereals tend to be the red ones, which happens to be shelf number 2. Now, what are trends that typically one can find with these kinds of plots beyond what I just showed you? Here's a potential trend that you would see amongst 3 variables. Would you call this a positive trend amongst all 3 variables or a negative trend amongst all 3 variables? Positive. Okay. Now, obviously between x and y, if we have 2 variables, x and y, it's obviously to see that's a positive trend. But let's say if we have a 3rd variable, we'll call it z, which corresponds to the size of the plotting point. Notice that as x increases, the bubbles get bigger. As y increases, the bubbles get bigger. Here's an example of a plot where there's no trend between x and y, but then they both have relationships with that 3rd variable z. Because as you get closer to the middle, let's say, you have bigger plotting points. So eventually for project number 1, what you're going to do is show me that you understand how to do a bubble plot. So you'll pick like 3 variables that you think is appropriate for your particular data set. And you're going to do a plot. You're going to try to interpret it the way that we've done here. You're going to need to try to maybe add, let's say, color to it if needed. And just demonstrate to me that indeed you can reproduce it and you can interpret it. Here's an example of a bubble plot that I have found very useful in some of my own work. Bubble plots are often used for, you could say, diagnostic measures in terms of a model. Let's say you have some kind of maybe a regression model. You want to determine, is my regression model a good fit? And so if you had just let's say, a normal linear regression model, and if you had Stat 870-like course, you would have talked about this. And in Stat 801, I guess I would also talk about it. Here's a scatter plot between x, let's say my explanatory variable, y, my dependent variable. And if I had a model that goes through the middle of those points, I can see the points follow pretty close to that line there. And so I think I have a good fit model. But instead, if I have other points that are out here as well, then you might be thinking, okay, that X is not necessarily a good predictor of Y. Well, for other regression models, though, unfortunately, the same kind of interpretation cannot always be used. And in particular, there's a type of model that we'll be looking at later called a logistic regression model. Maybe some of you have had experience with it in other classes, but definitely that is not a prerequisite for this course. And so what I have here in red is a logistic regression model for the place kicking data set that we looked at earlier in the course, where let's say I use the distance of the place kick to try to predict the probability of success for the particular place kick. So estimated probability of success is on the y-axis, distance is on the x-axis. If you just focus on the red line alone, you notice that as the distance increases, the probability of success goes down. Okay. Now, I like to examine this kind of, well, let me back up. So a way to assess, does my model fit well, is that you might want to, let's say, plot, let's say, the proportion of successes at each distance. So for example, for 18-yard place kicks, there was one failure, 2 successes, so the observed proportion of successes was 2/3. For 20-yard place kicks, there were 776 successes out of 789 different, let's say, attempts. Why is there so many there? Well, at least back when I collected this data a number of years ago, the rules in football were that point after touchdowns, which is a particular kind of place kick, would always be from 20 yards. So that's why there happens to be lots of place kicks at that distance comparatively to the others. And so we can see here that we have some situations where, for example, there was 1 success out of 1 attempt at 56 yards. Not a whole lot of kicks were done at those later or longer distances. And so if one were to, let's say, look at those longer distances, and we see we had some 1 out of 1s here, we had some 0 out of 1s down there, and I make the size of the plotting point correspond to the number of place kicks at a particular distance, we can see that we have some big deviations from this model. And you might be thinking, well, wait a second, this model doesn't fit the data very well if one were to use the original interpretation I had that I talked about at the very beginning. But instead, what one needs to do is take into account the fact that, with binary outcomes, simply you're going to win some, you're going to lose some. Even if you have, let's say, an estimated probability of success of 0.9, 0.95. At times you're going to miss some of those place kicks. And so by doing a plot like this that allows you to take into account the plotting point size, in terms of a bubble plot, correspond to the number of place kicks attempted there, then I'm not really worried about having such a large distance there, because I can only be here and I can only be there. That's it. I'm always going to be far from it. And even, let's say, remember that 18-yard place kick? I had 2 successes out of 3 trials. Now, if you're a football fan, you know that you're going to have a high probability of success there, but at times they are missed. And it just so happens since I only had 3, and I had one of those times where I missed, or whomever missed, I wouldn't miss. That one miss, it takes me down from an estimated proportion of successes of 1 to now 0.67. And so I'm not worried about that at all. What I look at then in this particular plot is I'm looking at especially the larger circles. If they are having some maybe deviations from that line, then I'm a little bit worried that maybe the model's not fitting well. And it's not necessarily clear cut on these plots to make a formal judgment, but at least allows you to start saying, okay, I want to maybe take a look at these 32-yard kicks a little bit more and see if I can figure out, why is this happening? Maybe, for example, there's another variable out there that's leading to having, let's say, fewer successes that I would expect based upon where the model says my number of successes or my probability of success should be. And so I have found this kind of a plot to be very helpful in that regard. Notice this large circle here. That corresponds to that right there. And so this was actually the first time when I did a bubble plot where I found out, oh, there are times where it's helpful to do a rescaling. Because if I actually did a rescaling of these, the number of successes for in terms of the size of the bubble, if I wouldn't have done that, I would have had one big bubble here and everything else would be just simply dots. So, lastly, you can take a look at this on your own. There's about, I think 10 years ago, there was this video that went viral of somebody actually using a bubble plot to help demonstrate some stuff. I won't get into the details here, but maybe you might remember this. This guy here talks about 200 years that changed the world, where he has, let's say, life expectancy on the y-axis. He has
slowly health was getting better, and when
income level, the bubble sizes correspond to, I think, population. And he puts a fourth dimension on it, time. And so this video then actually goes through time and shows you what happens with these bubbles. And so this was a great example of how bubble plot can be very helpful to explain things. Okay, so I'm going to end it here. And let's make sure we understand what's happening next in our course. Oops. Okay, obviously I'll have my office hours after class. Thursday, of course, we'll have the test, and again, start at 8 a.m. Just to give you extra time if you need it. Looking further ahead, next week we will start talking about the project. I will put it on my graded web page, and once I do that, I will, or the form will write up the project. Once I do that, I'll post a message to the discussion board. And if you really want to look really farther ahead, test number 2 is Thursday, October 19th. Okay? So that is all here for today.